Howdy, folks. How's it going? Yeah? Awesome? Sweet. Excellent. We got a couple of people coming in, but I think we got quorum. We're going to call this ready to go. So first, foremost, just to make sure you're all in the right place, getting great performance out of Cordova apps. We're here to talk about really not just Cordova apps today, but a lot of this is going to apply to web applications as well. So if you're not already a Cordova or a PhoneGap developer, sweet, you're still in the right place because a lot of these lessons will still apply. Please do not forget to submit evaluations. I take your feedback extremely seriously. I speak a lot and want my presentation to be better. So please, give me your feedback. Let me know how things went. If you're here today, it's because you probably spend enough time working on mobile applications that you care at least enough to spend the next hour learning how to shave milliseconds off of users' experience of your app. So seriously, give yourself a round of applause. You're deep enough into it. Yeah, you care about perf. Awesome, good for you. But today we want to change some of the perceptions that may be out there that Cordova apps or web applications just can't cut it when it comes to kind of native-like performance, because it can do it. It can do it. Why? Because of science, right? So here's the deal. This talk here is really the result of about 3 months of science experiments where we really kind of went out and talked to developers, analyzed some apps, saw some kind of basic problems in essential coding patterns with Cordova applications. Then we went out and we talked to kind of some of the bigger and best framework developers out there, the Ionics of the world, and the Kendos of the world, and the WinJSs of the world, and learned how they did it, and then kind of compared common practices to best practices to see whether or not those differences actually resulted in meaningful perf differences so that we could better understand what exactly it is about Cordova that sometimes, causes it to edge a little bit. One thing I am going to say here, guys, this is a relatively good, strong group of developers in the room. I want this talk to be a practical talk and a conversation among developers. Let's geek out for the next hour. If you want to interrupt me and ask questions, please do so. I'll repeat it for the room, and let's just learn how to be smarter, better developers. Cool? Yeah? Awesome. Sweet. All right. Let's just start with a little bit of the basics, just to level set. For those of you that are not already familiar with Cordova, here's the basic idea. It is essentially a web application written in HTML, CSS, and JavaScript, but it lives inside of a web view. And it gets access to native device capabilities through these things called plugins. When I say native device capabilities, what I really mean are things like, the camera, geolocation, accelerometer, device contacts, things like that. The basic model, like I said, is that it lives inside of this web view. Because it lives inside of a web view, it needs to communicate through the native code via an asynchronous call. That asynchronous call basically talks to the native code. The native code returns back a response. In the case of a camera, just to make things simple, it returns back a base64 encoded image or reference to the file URI in the library, and then your web app can go about doing its business. Typically, not always, but typically, all of the HTML, CSS, and JavaScript is packaged with the application so that your web app, your hybrid app, can also operate in offline scenarios as well. So the first part of the talk here today is going to focus really on kind of the Cordova piece of it. The second half of the talk today will apply to Cordova, but it will apply equally well to web applications if that's your primary focus. Yeah? All right. So before we kind of get into what is good performance, let's define what we mean by snappy and fluid and responsive. So typically, there's a lot of different kind of classifications for this, but if you kind of average it all out, people typically think about performance in interaction classes or categories. Over towards the far left-hand side of this chart, you'll see fluid. That's 17 milliseconds. If you do the math, that really calculates to about 60 frames per second. That sound familiar? We're all trying to chase after that golden 60 frames per second. So that fluid class is less about user interaction with your app and more about users' perception of your app. So this is animations and transitions and the like. One to the right, instantaneous. This is really about when you touch the kind of the screen and maybe the button automatically lights up, or you touch and drag and the object sticks to your finger, or you swipe and you get a smooth transition. So that's kind of in that 17 to 100 millisecond category, the golden somewhere probably around 50 to 60 milliseconds. One to the right, you've got fast. This would be for macro level interactions that change large parts of your UI. So think about this as a navigation event, if you will. And then everything to the right of that, you better throw up a spinner. This is where things are getting really long, and maybe this is because you've got to make a data call over the wire, or you've got to do some heavy data processing in the background. Today, what we really care about is the far left-hand side of this chart. Because frankly, everything beyond 250 milliseconds, there's no question that HTML, CSS, JavaScript, web technologies are able to handle it. It's really kind of in that far left-hand side. So that's where we're going to focus. I already said earlier, methodology. Basically went out and talked to folks like you, compared it against some of the best developers and framework makers out there. And that essentially gave us, by the way, all of the tests that we performed here, in order to compare it against iOS, Android, and Windows, we chose 3 relatively comparable pieces of hardware that aren't the newest, aren't the greatest, but they were pretty gosh darn good when they came out like 2 years ago, 1 to 2 years ago. And so all of the experiments were conducted on these devices. Your mileage may vary depending upon the actual device that you're targeting, but the same basic principles will apply. So through these experiments, we got 6 different kind of classes of issues that kind of are common pitfalls that developers fall into. The first one, the web view tax, I'll talk about. That's the one that really primarily has to do with Cordova development. Everything beyond that will apply equally well to both Cordova, PhoneGap development, and web development. Savvy? Yeah? Sweet. All right, web view tax. So I talked earlier about the basic architecture of a Cordova application, that it runs inside of a web view and that's wrapped inside of a native container, that native container being written in Objective-C for iOS, Java for Android, fortunately native JavaScript for Windows. But because you run inside of a web view, there's going to be some overhead, right? And so that's the tax. This is what you can do nothing about as a Cordova developer. You just got to pay it. Right? So let's understand what that's about. Here's what we did. We said, okay, because a Cordova application is essentially a web view inside of a native application, it makes sense to instantiate that web view might have some memory overhead. Makes sense, right? So maybe the actual memory overhead for being in a Cordova app is a native application plus a browser, and that equals a Cordova app. Seems intuitive, right? So here's what you see here. Each of these orange bars is a native application, a hello world application, if you will. Nothing is running whatsoever. And this is the memory footprint for each of the operating systems: Android, iOS, Windows Desktop, and Windows Phone. Then what we did is we started up a browser. This is like Safari or Chrome in the case of iOS, and Android IE in the case of Windows. And we said, all right, what's the memory footprint of just the browser displaying about blank? Okay, so A plus B equals C. Native plus browser equals Cordova. Not so fast. That's actually not the case. I want you to pay attention here. I'll skip over Android for a second. iOS, Windows, and Windows Phone. Those are kind of, the Cordova app is roughly equivalent to the native app, or at least not so far away that it becomes really dangerous. The far left-hand side, that giant World Trade Center tower that is the Android memory footprint, I want you to remember that for a second. And actually, remember that for the next hour, or the rest of your lives even. All right, so here's the thing. I started talking about memory, but you guys may be saying memory ain't got nothing to do with performance. It's invisible to the user. You're absolutely right, but it does have an impact on the user. And one place to see that is in startup time. So here's what we did. We took each of the devices and we took a high-speed camera filming at 240 frames per second. And then we divided that, that film up into individual stills, each of those stills being roughly equivalent to 4 milliseconds. Then we went from the exact start time of the touch, and it may be a little bit hard to see on the screen, but when I'm touching that Hello World app, the icon's got a little bit of a glow around it on the left-hand side. And on the right-hand side, you can start to see the kind of zoom effect that's going in. That means that the app is initializing and starting up. Counted the number of frames in between start and launch. 133 frames times 4 milliseconds per frame equals 532 milliseconds in this particular example. So let's take a look at what the actual results were. So on the iOS, and notice the asterisk next to iOS cold for just a second. That big tower I want to caveat in a moment. But for iOS and Windows Phone and Windows Store, the results were roughly the equivalent of the native app, right? On the Android side, you've got two large towers there. Those green bars are the Cordova apps. So your startup time in Android, where there was a significant memory footprint, was much slower. That's not so good. That's one heck of a tax to have to pay. The large bar that's there for iOS native, I want to caveat that with the asterisk by saying, because we use the default Hello World template for iOS, and that default template has a built-in 500 millisecond delay before launch that most developers would override, that length of time probably isn't accurate. We probably want to go back and retest that because my guess is that if we retested it, it would be much lower. For each of the platforms as well, you'll see that there's a cold and a warm start. A cold start basically means that we completely shut down the device, then started up the device and immediately started the application. A warm start means that we started up the device, then started up the application, then shut down the application, and then reopened the application. There are kind of startup time differences clearly between the warm and the cold in some cases. So you got a bit of a tax here to pay, particularly in the Android ecosystem. As a Cordova developer, there's just not much you can do about that. But for iOS and for Windows, good times, right? All right, so startup time is not the only place where you pay a tax, though, in the Cordova ecosystem. There's also that bridge that you have to make between your web code and your native code, right? We had to make that plugin call over to the native code to go get the camera data or the geolocation or the accelerometer data or whatever it was. So here's what we did. We built a dummy plugin, and that plugin's only purpose in this great big world was just to receive data and send it back. It didn't do anything complicated, just received it and sent it back. And we measured the amount of time that it takes to kind of travel over and back from that bridge. And here's what we found. We found a pretty linear progression in the amount of time that it took as the amount of data increased. But here's the kind of important point that I want to make here. To transfer a 10 to 15 megabyte image across that bridge, it's in that 200 to 300 millisecond range. In other words, it is in what you would call like the fast range in our previous interaction classes. To transfer anything like geolocation data, accelerometer data, that kind of stuff, you're back in the 4 to 8 millisecond territory, right? So it's below instantaneous. It's like super, super fast. So kind of the takeaway that at least I got from this was that bridging that web view was pretty much free, right? It didn't sort of appreciably impact performance at all. And that's great news. That means that the perf tax that you pay for being a Cordova app is virtually nil, except for in the Android startup case, and that's only for startup. Okay. So let's move on to the larger class of performance issues that we found both with Cordova apps and with web apps. And these are a lot of the same issues because, well, frankly, your Cordova app really is a web application just running inside of a web view, inside of a native container. And the first place we're going to go to is the DOM. We all know and love the DOM just as much as we love our Seahawks. They are, it's the objects that live inside of our application and make UI, right? So here's what we're going to do. I'm going to show you guys a demo. This is one instance of the experiments that we ran. I want to be clear. All of the experiments that we ran them thousands of times. I'll pause that real quick. We ran those thousands of times in order to get a kind of nice, statistically relevant sample size. What I'm going to show you is one of those instances, and I'm going to show it specifically on an Android device that is tethered to my PC, and then I've got an application called MobaZen, which essentially does screencasting back to the desktop. So everything you see is actually going to be performed, in this case, I believe, on a Nexus 9. And here we go. All right, so this first one is comparing a simple DOM versus a complex DOM. What I'm doing is I'm opening up the tools for Apache Cordova here, and we're going to have a couple of different examples. And one of these guys, we're going to be launching and kind of modifying a relatively simple DOM that has, about 100 elements, and they're not too deeply nested. Next one, we'll be using, the next three actually, we'll have a complex DOM with many more elements, and we'll be injecting them and modifying them using three different techniques. One of them using inner HTML, just shoving it in as a string. The other one using kind of a pen child and document create, or create element. And then the final one using document fragments, where we make the modifications outside of the DOM and then inject it wholesale into the DOM as one action. In the console here, I'm outputting the results. And you'll see that for each one of them, I have a median and an average that I'm capturing. When you're doing perf tests, it's generally the median that you want to go after. And right there, I'm going to stop it for just a moment to highlight that. Notice that the median for the simple DOM modification is that amounts to 0.026 milliseconds. I know that's not much. That's not much at all. But keep that in mind, because it's going to, when you compare it to the complicated DOM or the complex DOM using inner HTML, which is at 0.054 or nearly double that value. Those small numbers are going to add up big time later on. So if you take anything away from this particular experiment, it should be that the fewer the number of elements that you have, hey guys, we can watch Russell Simmons. Sweet. Success through stillness. That sounds awesome. Maybe afterwards. If you take anything away from this, really reduce the number of elements that you've got on the page and reduce the complexity of your DOM. Let me give you kind of a code example of what that would look like. That looks pretty normal. That looks pretty friendly. It's just a list item with anchor tags. But when you're making decisions to optimize for performance, the decisions that you make are not going to be the same that you make for code legibility or even kind of readability, any of that. In this case, I've actually reduced the number of elements in my DOM by about 30% or so, just by reappropriating those list items and attaching an event to them, right? So not entirely intuitive from a kind of an initial code legibility perspective, but from a perf perspective, really, really important. Okay, layout thrashing. So this is basic idea here is that we're going to have a loop, and at the point where we set a CSS value, we are also going to read that CSS value directly from the DOM. That is called layout thrashing, because as you go through that loop, every single time you're going to have to make both a query to your layout engine to say, what's my size, and then you're going to reset it. And doing those over and over and over again, it can really kind of tax you. So let's see how that works. Same principles apply again. I'm going to launch this guy using a Nexus 9. And notice here, there we go on the left-hand side. I'm setting it, and then I'm reading it on the right-hand side inside of a for loop. Then I've got another experiment where this time what I do is I'm going to read it in one for loop, and then I'm going to set it in another for loop by essentially storing those values into an array. So here's what we're going to do. In this first one, I believe the first one here, we've got, this is the one where we're going to do thrashing. And look at the amount of time that took. That took nearly 4 seconds, 3,814 milliseconds. Then I just reset it. And then I did the fast method, only taking 56 milliseconds. Let's pause this guy so you can see it. So that slow is where I'm doing a for loop where I'm setting it and reading it on either side. The fast one is where I do first a loop to read it, and then a second loop to set it. That cut my time by, is that 20%? I don't know, I'm not good at math. Yeah, 20%, something like that? No, even less, like that's 5%, right? So huge, huge improvement just by refactoring your code a little bit there. All right, back over to this guy. So if you take any lesson away from this piece of it, batch your layout operations together. Bad, don't do this. Good, yay, good work, right? Batch them together. All right, so we talked a little bit earlier about the number of elements in your DOM and the complexity of your DOM really kind of impacting the performance of your app. And one of the places where that manifests kind of most obviously is when you've got a long list of thousands of items and you try to scroll through them quickly. Now, there's a, most of you, I'm sure, are familiar with a thing called virtualization. The basic concept of virtualization is this, that you've got a screen, and rather than load in all, I'm going to call it 1,000 elements, right? Instead, you just load in those elements that are visible on the current screen, plus maybe 2 or 3 screens on either side of it. And all the other elements typically get replaced with a single dummy element, and therefore it doesn't have all the children elements in it, or some other trick in order to maintain the scroll position. A good example of that, many of you I'm sure are familiar with Facebook, and when you first kind of bring up the mobile application, you might see a gray box there before the content actually loads in, and then kind of as you scroll down, you might see other gray boxes appear when you scroll quickly until they load in. That little magic trick is called virtualization. So here's what we're going to do. We're going to look at a virtualized list compared to a non-virtualized list, where we're essentially seeing what happens when you've got thousands upon thousands of elements in the DOM and in a non-virtualized list. And then in the second one, in a virtualized list, where that DOM has been programmatically simplified through virtualization in order to provide a better user experience. In this particular case, I'm going to be using When.js. All right. Got the first one loading in here. And if I'm not mistaken, this is the non-virtualized list. So remember, I've got my Nexus 9 here. I'm scrolling, scrolling, scrolling. Well, damn, that whole thing just turned white, right? The reason it turns white is because the rendering engine just can't keep up with it. As you're scrolling, the paint cannot happen fast enough because the web view, the browser, it's got too much to do. It's got too many elements to try to calculate. Okay, so that was the non-virtualized list. Let's see what the user experience is like inside of the virtualized list. So in the virtualized list, and here we are once again, I'm using When.js. You're still going to get a little bit of that, I'll call it tearing, right? But this time, instead of getting kind of an empty blank white screen that looks like the application's just become unresponsive, instead, what we're going to see is we're going to see some gray boxes that show up. Let's fast forward a little bit. Oh, there we are. Now it's up. Come on, virtualized list. We're going to see some gray boxes that show up. And those gray boxes, in terms of providing feedback to help users know, yeah, you can see them the gray boxes come up at the bottom there. There we go. So now I'm scrolling super, super fast. I believe this list, if I'm not mistaken, might have had, it was either 1,000 or 10,000 elements in it. And so you still end up with some of the a few elements that are not visible, but because your application is providing feedback, is letting the user know like, hey, there's content that's loading in here, the perception is far, far greater and far better. All right, Let's shut that one down before we have to watch Russell Simmons again. And here, I talked early about the kind of the memory footprint, and remember Android, how that giant kind of bar came up and it had a slower start time. Here you can see kind of memory correlating with the performance of the non-virtualized versus the virtualized list. In this case, the virtualized list has about, what is that, about a third or so of the memory footprint of the non-virtualized list. And that's due in large part to kind of the reduced number of elements that are in the DOM. Awesome. Okay, so takeaway here, use virtualization. A lot of kind of popular control frameworks provide this. Ionic, WinJS, Kendo UI, Onsen UI, all those guys provide virtualization, and you should use it. It's really hard stuff to write. You really need a team working on it. This is not a roll it yourself kind of thing. Or at least I wouldn't want to roll it myself. Okay, images. This is another excellent example of when you've got maybe a different decision that you would make for performance than you would make for kind of convenience. And here's the thing. So in the last, 5 years or so, CSS has made a lot of strides that make it way, way easier to do the stuff that we used to do in Photoshop directly in the CSS. And gradients are a great example of that. If you want a gradient, you don't always have to go and create it in Photoshop and then create like a 1-pixel tile to put out there. You can just create a gradient in CSS. Well, let's see what the perf difference is between these two guys. So for this one, what I'm going to do is I'm going to take an image, actually not an image, a div. And in the first case, I believe the first one uses a CSS gradient, if I'm not mistaken. And you see we've got it here for each of the different major kind of browsers. And the second one, I've got a div where the gradient has been created via a bitmap. And what I'm going to do is I'm going to animate that guy across the screen. For this one, I'm bringing up my good old friend, the Chrome development tools, to do a perf measurement of it, since this is an Android device. And for those of you that maybe have not used the perf profiling tools inside of Chrome, I'll actually pause it here in just a sec. Those bars there, those bars are telling you what your frames per second are. Let's pause it so we can actually see it. Those bars are telling you what the frames per second are. You do not want those bars to be tall. The taller the bars are, the lower your frames per second, and that's going to provide a more stuttery type of experience. You want low bars, ones that are low to the ground. In the kind of, you see that the left-hand side, we've got frames per second that are well below 30 frames per second. I'm guessing at its worst, that was probably 15 frames per second, maybe even less than that. On the right-hand side, when we're animating the image, we're getting frames per second that are closer to 45 to 60 frames per second. That's all goodness right there. That's magic. Let me give you kind of why I think that is. And I haven't kind of peeked under the hood in Chrome or IE to confirm this, but what I think is going on here is that in the case of CSS, as it's animating that gradient, it has to recreate the bitmap on each frame. In the case of the image, that bitmap has already been created once, and it just needs to move it from position A to position B. So recalculating that bitmap on each frame is super painful and causes a significant degradation in performance. So when you are optimizing for performance, you may want to end up using an image for your gradients rather than CSS. And this comes not just for gradients themselves, but also for drop shadows or anywhere else that a gradient might be used. Nope, we got to exit out of this guy. All right, back over to it. So, yeah, totally. Yeah, so the question was, would I apply the same principle to my jQuery animations? And generally, yes, I would. I've not done a test on this with opacity. So I would want to do a test to see if the opacity, if it plays differently. But certainly, like, this holds universally to be true. Okay? All right, so bad, don't do this. Good. Good developer. All right. Animation. All right, so animation, this is really all about getting that 17 milliseconds, 60 frames per second thing again. I know before we were kind of talking about images and CSS. This is going to apply to elements however you're using those elements. And really our goal here is to move as much of the processing over onto the GPU as possible. Because JavaScript being and rendering being kind of a single-threaded kind of thing, moving it over to the GPU clearly gives you the opportunity to do kind of doing more with multiple threads. So we're going to take a look at using transform versus position. And this one, I'll be honest, I would guess that probably 80% of you in the audience might already know this one, but it's a good reminder and good to get back to fundamentals nevertheless. In this particular one, what I'm doing is I've got two different animations. And the first one, I'm animating using top and left, although the same thing would apply for any property that affects layout, margin, padding, border, anything that is going to cause a reflow in your document model. And the second one, I'm going to animate using CSS. So let's see here. First one, actually the first one I did using CSS. That was using translate X and Y using 3D transforms. Okay, and that one, you saw that I got nice low bars. Now I'm animating using position, and look at that, I've got all these wicked tall bars all along the way. That's because the browser's having to recalculate layout with each one of those. So when you are animating, if it were not already amply obvious to you, please, please, please use transform, use translate, rather than anything that's going to affect layout. It's going to reduce your frames per, or actually increase your frames per second, double, trifold. Yes, sir? That one was 3D transform, yes, sir. All right, so bad, don't do this. Good, translate. All right. Now, there's another way that you can animate, and a gentleman here up front was just talking about using animation via JavaScript, and we do it all the time. It's a great thing to do. There are some real practical use cases, besides just kind of the convenience of saying fade in, fade out, that you might want to use JavaScript animation. For example, when you need to redirect an animation midstream, and you don't necessarily want to have just a pre-calculated animation that fires all the time. So it is not necessarily the case that you will always only want to use CSS animation. There's some real use cases for JavaScript. But what are the best ways to do that when we need to do it using JavaScript? So in this particular one, we've got a couple of different types of animation that we're going to do. In this particular one, we're using, let's see, we've got first a set timeout, and then by an interval. Right? So we're just kind of iterating every 60 frames per second, either using a set timeout and resetting it, or via an interval. Then we've got another one that's going to use the request animation frame from your CSS timer. And then we've got another one, again, that's just going to use a pure CSS animation. Is everyone familiar with request animation frame? Essentially, for those that don't know, request animation frame is essentially a timer that runs in CSS, and it's kind of the CSS equivalent of an interval that's running, but it doesn't have to be on the JavaScript thread. All right, so that first one, I believe, that one was with set timeout and set interval. And all of these are using the top and left position. So we're doing the bad practice of animating position via X and Y. All of those, as you might guess, are giving us frames per second of 30 frames per second or less, so not very good. The next one that we're going to do here, oh, and I love this one. I believe this is where Chrome actually kind of bugs out and gives me weird results. So now we're animating via CSS animation, and it's kind of hard to see all the, actually you cannot see all of the bars because they're just not rendering correctly. I do it multiple times trying to get Chrome to actually render correctly. But that CSS animation is super fluid, and in this one, we're actually getting frames per second that are around 60 frames per second, maybe even a little bit better. Oh, this one, I finally got it. There we go. We see all those threads at 60 frames per second. The next one here is going to be with request animation frame. Oh, I was a bad boy and did not actually record the request animation frame. I'm sorry about that. I can tell you the results, though, because I did it 1,000 times over. The request animation frame is the exact same frames per second that you get with CSS. So even though it's done programmatically via JavaScript, and you're just setting it, in this case my translate 3D on each frame, because I'm using the CSS interval, the request animation frame, to manage my loop, I get way better performance, right? So if you take anything away from this, take this away. Use either request animation frame or CSS when you can. The benefits there are just magnificent. Okay. Garbage collection. Everybody loves their garbage collector. Takes all the dirty stuff away, right? So garbage collector, we've actually got many, many years of the browsers perfecting their garbage collection. They actually do a pretty gosh darn good job of it. They kind of, when we remove our elements from the DOM, they remove them completely, and we don't accrue any kind of memory debt. But the fact of the matter is that you can code yourself into a corner where the garbage collector doesn't know where to find your trash. What that results in is accrued memory over time, and we've all seen over the course of the last 30 minutes or so what happens when you accrue memory over time. Your performance generally starts to degrade over time as well. And in browsers, this is less of a big deal because, frankly, you're tearing down your browser every time you navigate to a new page. It's doing a complete memory dump. But when you're in a Cordova application where you rarely shut down the application, I don't know about you guys, but I can have applications running for weeks or even months before I actually restart my phone. That kind of accrued memory debt over time can be very, very painful. So let's try this first one. In this particular one, here's what I'm going to do. I'm going to create a bunch of elements. I'm going to attach an event listener to them. And then I'm going to get rid of the elements just by doing inner HTML equals quote, quote. In other words, I'm purging the element. But I still have all of those event listeners and the functions that are associated with them hanging around. So still on my Android device, I'm going to go back over to the Chrome DevTools, and this time I'm going to do a kind of a memory analysis of it. What I'm doing here is I'm just creating and attaching those event listeners and then destroying the elements. What I want you to pay attention to is this ramp right here that's slowly growing. That ramp is performance death, right? That's just your memory growing and growing and growing until eventually your application will slow to a crawl, and it will happen. Your application will eventually just straight up crash the browser. Now, I know that I was adding thousands and thousands of elements very quickly at a time, but as I said before, if you've got an application that's up and running over the course of multiple weeks or months, and you're doing lots of navigation and leaving those event handlers around, that can be very, very bad. So be good. Remove the event listeners. Make sure that you've kind of eliminated all of your debt so that your memory does not grow over time. Bad. Don't do this, right? Don't leave those event listeners hanging around. Good. Go ahead and be responsible. Remove that event listener, remove that element directly from the DOM using the tools that the browser gave you. All right. Now, when it comes to event listeners, it's also important to minimize the total number of event listeners because each one of those functions has a memory footprint in your application. And there's a couple of different ways to do this. So one way, and I do this all the time, I'm sure all of you do as well, I've got a for loop, and I've got an array of elements, and I just loop through that array of elements, and I say add event listener function, and then I write the function in line, and then I loop through the method again, right? And so I end up with a one-to-one pairing between my objects, my elements, and my event listeners and their functions. There's a better way to do this, though. The better way to do this is essentially to use event bubbling. Through the magic of the DOM, you can basically have a single kind of method at the top that's only on a parent element. And then you essentially have a switch case or an if statement that's in that method that identifies the click target and then executes that. That way you only have one function that handles events for everything. And I know, that from a maintainability perspective, that looks a little scary, that sounds a little scary. But so long as we're in a perf talk, talking about ways to optimize for performance, this is a decision you may want to make in order to optimize for better performance over code maintainability or legibility, right? So let's see what that actually looks like. Oh, here I actually explain it a little bit better here. You see here that I've got these objects or elements, 1, 2, 3, and 4. I can put an event listener on the dude, and that event listener will basically listen to say, click target is 1, execute function A. Click target is 2, execute function B, or execute code segment B. All right, let's actually see this in action. So in this particular one, I've got a page where we do, let's see here, got this guy launching up, where we're going to create a bunch of objects, or of elements, and for each one of those elements, we're going to first attach a, actually the first one we're going to do is going to use the bubbling. So we're going to use the good way first. Let this guy get started up. Here I'm kind of passing you through the code here. So in this one, I'm going to hit 1 event listener, that's the top one. I know it's a little bit difficult to read, but trust me, what we're doing there is this is the event bubbling one. Click on that guy. Awesome. In this particular case, we're going to take a heap snapshot to see what the total memory footprint of the application is. And this will give us an idea of kind of based upon a kind of a correlation with memory, what our performance over time might be. All right, the next one, we're going to use 1 event listener and 1 function per element. So this is the method where we had a for loop, and we just looped through our array of elements and assigned a new function to it as we went through the loop each time. Okay, that gave us our snapshot 2. And then finally, this last approach that we're going to do, this is going to have a for loop again, but instead of each time defining our function in line, we're going to reference back to a single function that's been identified separately elsewhere. And what I want you to pay attention to on this, we're going to highlight it in just a second, is look at this number right here. This is it's about 8% of the total memory allocation. That's correlating to 257 kilobytes. This one is double. This is the 1 event listener and 1 function per object. And then this is the event bubbling one again, back down to 257. So by creating a unique function for each event listener and each object, we effectively double the overall memory footprint of the application. And here you'll see I'm kind of opening it up, and you'll actually see the event listener and the prototype function that's associated with each one of those objects. Even though each of those only has 264 kilobytes associated with each one, or maybe it's bytes, 264 bytes with each one, because that adds up over time, it creates a significant footprint on your application. So if you take anything away from this, I would say take advantage of event bubbling. Or failing that, if you're not going to take advantage of event bubbling, at least reference back to a common function and use that common function to kind of sort things out from there. Don't try to stamp out and replicate your method for each object. So, bad. We got that for loop there. We're kind of assigning and creating a new function for each object. Good. Reference back to a sort of a function that's defined elsewhere, or use event bubbling inside of your DOM. All right? Okay. Pay attention to memory leaks. So this is kind of similar to the lesson that we saw earlier with when we kind of wiped out our DOM, but we left all of our event listeners there. But in this case, it's kind of the HTML element corollary to it. There we go. Open this guy up. And in this case, what's actually going to happen is that in the first case, we're going to have objects that map to a private function. And so when we navigate and we kind of get rid of that function, all the objects are going to die with it. In other words, they won't be kind of orphaned in the DOM, right? In the second case, we're going to attach all of those to a global namespace. And because it's in a global namespace, when the private method dies, all of the objects will still be sticking around. And because they're in the global namespace, polluting that namespace, they're just memory dead again. So in this case, I'm navigating back and forth, and like I said, in this one, we're attaching all of the objects to a private method whose lifetime will expire with the navigation event. Here we take the snapshot of it in the Chrome DevTools, and you'll see here, I'm going to kind of look at my HTML div element there, and it's nice and clean. There's nothing superfluous there. All of those elements are actually being used in my DOM actively at that moment. In this next one, I'm going to do the same thing, but like I said, this time all of those elements are attached to a global variable. That global variable, because this is a single page application, does not expire with the navigation event. So I just did that in this case by removing the var declaration inside of the function, automatically placing it in the global namespace. So here we go again. We're going to do launch the application and do navigation. Theoretically, that should, if it were in a private namespace, it would have gotten rid of all those objects. I'm going to fast forward a little bit because you know what navigation looks like. OK, here we go. I'm just doing a second heap snapshot of it. And in that particular one now, when you look in the DevTools, you see all those elements that are red, kind of got like a pink highlighting to them. That means that those are orphaned elements that exist only in memory, but do not exist in the DOM. You don't want that. Over time, those guys are just going to build up and build up and build up, especially in this case when it was on a simple navigation event, and that's just going to load down your application and cause it to get sluggish over time. All right, we're closing in on the end here. So to destroy all those unused objects, keep them out of the global namespace. When you know that you're not going to use them anymore, responsibly remove them from the page. Bad. In this case, see var L is in the global namespace, and then I'm creating it and then potentially destroying it in a private method. Good, I'm both creating it and eventually I could destroy it inside of the private method, and so it's not going to linger around in that global namespace. Cool? Yeah? Awesome. All right. Last little bit of it here. So this is an interesting experiment because I've talked to several people in the last week about this experiment. So some of you may be familiar with this thing called fast clicking. So in a lot of versions of operating systems, particularly in Cordova apps, this is really relevant to Cordova apps. A native application, when you touch, it immediately fires the click event, usually within, I don't know, less than 50 milliseconds, let's call it. But for what were some actually relatively good reasons, in browsers, they delay that click event by 300 milliseconds. Ostensibly, the primary reason is that you guys have all done this before. You kind of double tap in your web browser because you want to zoom into the HTML text. That's a good usability feature, right? But the fact of the matter is that in a native application or a Cordova application, you want it to feel more like a native application. So you don't want that 300 millisecond delay when you click. You want it to automatically register as a click event. There are a number of frameworks out there that have been designed to kind of solve this problem by essentially mapping the click event to the on-touch event or the on-mouse down event, depending upon whether it was a touch device or a click device. One of the most popular of these is called fastclick.js. And so we did a bunch of experiments trying to reproduce this 300 millisecond delay. I'll be honest, in our experiments, we were not able to replicate it. I feel like we must have done something wrong, but there it is. We were not able to get that 300 millisecond delay, and here you'll actually see it. I'm going to launch an application on in this particular demo, it's a Nexus 9, but recall that most of our hard experiments were on a Nexus 7 for the Android device, and an iPad Air for iOS, and a Windows 930, I think, for Windows. And what you're going to see is you're going to see when I touch this, and remember I'm touching this with my finger on the actual device, I see the touch start, the mouse down event, and the click event, and the delay that you see between there. And you'll see that I'm getting, what, on click event, I'm getting anywhere between 50 and 100 milliseconds. Mouse down, 74, touch start, 0. And don't get me wrong, 80 to 170 milliseconds is not nothing. There's still a delay there, but it is not the 300 millisecond that I've at least been led to believe. And so we're going to do a little bit more research into this to better understand it. As I said before, this is part of an experiment and a series of experiments that we've been running over the last 3 months, and we intend to continue it. I do have a question over here. That could be. I don't believe we had the viewport tag on there though. We tried to strip it down to the bare minimum. No, because it immediately registers it. So touch was 100% 0. Oh wow, that dude looks awesome. All right. Okay, cool. So we're kind of here at the end of it. I hope you guys have learned something. I hope that if it was a review, then it was a helpful review. If you leave this room today thinking anything, honestly, anyone can build slow apps. It's totally easy to build a crappy app. You can do it in any language, but you don't have to. Whether it's Objective-C, C#, JavaScript, anything, you can build a nice, snappy, responsive app. And I hope that you'll be able to use some of the lessons today to make your apps better. And if you've got any interesting experiments that you're conducting, please let me know. I'm on Twitter at Ryan J. Salva, and you can talk with the product team at VS Cordova Tools on Twitter as well. There are slides with practical advice at the end. These will be posted online. I will not rehash the last hour with you now. Does anyone want to ask questions kind of here at the end? Yes, sir. Yeah, so the question is, are there any static analysis tools for these types of defects? So there are some linting tools that are out there for it. I do not have any to recommend, but certainly one of our future research projects is to figure out what's out there and plug holes and what is not, so that we can start to provide some of those static analysis tools to provide better guidance to developers at the time of coding. Right here. So WinJS already provides for their basic controls, optimization to make sure that you're getting the event immediately. Other than that, all of the events are not specific to WinJS, at least to the best of my knowledge, but are rather just baked into the platform. And so I would continue. I believe that WinJS does the same trick that FastClick does to associate click with touch and mouse down so that you don't have a delay. Once again, in our tests, and granted these were all tests on 8.1 devices, not 10 devices, but the WinJS framework is the same, whether you're in 8.1 or 10. We were not able to find a significant delay using any of the default controls. Back over here. Yeah, so the question was, can I touch upon the impact of any of the more common or popular frameworks on performance? I will say that the Filament group did a fabulous analysis comparing Angular, React, I believe their third one was Backbone. Certainly, I would say that React definitely has, in their study, it won out over Angular, but not necessarily substantially so. With Angular 2.0 and even Angular 1.3 and above, they are really, really optimizing for mobile first rather than desktop. And so they are making huge strides to not just providing little impact to the perf, but also providing easy paths to fall into the pit of success with perf. I can tell you one of the biggest dangers that I see in enterprise environments is that over time we say, oh man, I want to add this other new feature. This framework over here has that feature. And then we, 2 weeks later, want to add another feature. And so we add maybe another little library, another little framework. And so what you end up seeing over the course of 3 to 6 months in an enterprise environment particularly is that you start to layer on jQuery, plus Angular, plus something else, and another plugin here, and another something there. And so layering frameworks on top of each other can be absolute death to the perf of an application. The other thing that I would say is that as you are considering frameworks, and in the Cordova plugin world as well, this is it's really anything open source. Please make sure that you are really responsibly evaluating the quality of the framework or the plugin that you're using. You can use some good proxies for that. You can look at the number of downloads for it. You can look at the number of contributions, the number of people who are contributing, and when the last contribution was. We had a customer who was using our tools recently who added in a plugin. It happened to be the most popular plugin for SQLite and use inside of Cordova for Angular. Had lots and lots of downloads, but the same plugin hadn't been updated in approximately 2 years, despite having a long backlog of pull requests that were submitted to it. In other words, the plugin had deteriorated in quality over time, causing terrible, terrible perf problems. And it was actually a relatively simple fix to kind of bring the plugin up to speed. But if you don't monitor the quality of your frameworks and your plugins, that can really wear on the quality of your overall application. So I would say, to circle back around to your initial question, any of the more popular frameworks out there today, like the big names of the world, the Angular and the React, the Backbone, the WinJS of the world, all of these guys are optimizing heavily for perf, and I would have absolutely no qualms with incorporating into my mobile application. At that point, it just becomes a matter of stylistic preference and a matter of compatibility with your UI control framework of choice. I think I saw another question here. Yeah? So the question was, he assumed, correctly so, that the perf analysis that we had done was on the default Android web view, and if we had done a similar test with Crosswalk. The answer to the question is no, we've not done similar tests with Crosswalk yet, and I very, very much want to. It is absolutely on our backlog. Here are the things that I can tell you about it. Crosswalk has about a 17 megabyte impact on your package size, so it will increase the initial install time. From what I understand, it does not have a significant impact on the runtime memory, and for reasons that I don't entirely understand yet, but I believe that what's happening there is that because the native Android application doesn't have to spin up Chrome, and instead the on-device Chrome, and it's just able to start up the Crosswalk Chrome, that the runtime memory impact is about the same. I have a suspicion, this is not yet grounded in science, I have a suspicion that performance in Crosswalk will be better than the older default Android web views, since you'll theoretically be using the latest version of Chrome, and it will benefit from all of the perf optimizations that you get in newer versions of Chrome. So that's my suspicion. Please stay tuned. We will be conducting experiments on this to get to the bottom of it and better understand it, so that we can all kind of make better choices there. There was another one that came from this general vicinity, I think. Maybe? No? Awesome, cool. Well, then thank you guys so very much for the time. Truly appreciate it. Don't forget to fill out the evaluations, and enjoy the rest of your time in San Francisco. I hope that you have an awesome time.